Hello everyone, welcome to the course on electromagnetic theory and interference. In this session, let us understand how to compute SWR, that is standing wave ratio, and the power of a transmission line. Before finding a standing wave ratio, let us understand what is voltage reflection coefficient at the load. Reflection coefficient gamma L at the load side is a ratio of reflected voltage wave, that is V naught minus e power minus gamma L to the incident wave at the load side. So divided by V naught plus e power minus gamma L, the ratio of reflected to the incident voltage waves. So we already know how to find V naught plus and V naught minus in terms of load voltage and current in the previous session. So we are going, after incorporating VL is equal to uh, we know that V equal to IR, right? So VL equal to ZL into IL here, and taking IL common outside, and if you substitute in this particular expression, V naught minus will be ZL minus Z naught into e power minus gamma L. Here it is plus gamma L. Both the terms get cancelled and we get e power 0, that is going to be 1. So total we get ZL minus Z naught divided by ZL plus Z naught, that is going to be the voltage reflection coefficient at the load side. Now we are going to find the reflection coefficient at any point on the line. So at any point means I should be able to specify not only at the load side the reflection coefficient at any point. For that, take a gamma of Z is equal to the ratio of reflected voltage to the incident voltage, same expression. Now before we have substituted L, right? Now we are going to substitute, because at the load the Z value is L. Now it is going to be Z only, and this e power minus gamma Z, when come to the numerator, it turns out to be e power 2 gamma Z. Now we are going to substitute instead of Ez, that is L minus small portion L dash. So if you substitute that, we get V naught minus divided by V naught plus into e power 2 gamma L, and that is the expression for load reflection coefficient. Okay. So voltage reflection coefficient at any point is equal to load reflection coefficient multiplied by e power minus 2 gamma L dash. The same manner we can find the current reflection coefficient, that is ratio of reflected current to the incident current, but it is going to be the negative of the voltage reflection coefficient at any point. When we know the reflection coefficient, we can compute the return loss. Return loss is nothing but the measure of reflected energy caused by the impedance mismatches. When the load is not matched to the characteristic impedance of the transmission line, ZL is not equal to Z0 means what happens? Some portion of the see, when this load impedance is not equal to the characteristic impedance, whatever the signal is incident, some portion will be reflected back. So I can measure the reflected power by means of return loss. Return loss is a measure of ratio of incident power to the reflected power, okay, which is measured in logarithmic scale. And we know that reflected power is nothing but the reflection coefficient magnitude square times the incident power. We know that reflection coefficient is in voltage term, it is reflected voltage by incident voltage, right? In terms of power means I have to square it, because P equal to V square by R, or V into I. In terms of V square by R, I am writing. So in that case, what happens here? Then it is coming in the negative side, right? So instead of P minus, if you substitute reflection coefficient square, P plus, what happens? P plus get cancelled. This 1 by gamma the whole square I can write like minus 20 log 10 of magnitude of gamma. We know that logarithmic rule, right? Anything in the denominator I can make it into numerator by adding by multiplying with a negative sign. So the reflection coefficient we already know, this one, ZL minus Z0 divided by ZL plus Z0. Okay. And the larger values of return loss will indicate there is less reflection from the load. And if there are no reflection, if reflection coefficient is 0, what happens? Log of 0 is infinity. Okay, return loss will be infinity. and this will be ideal case. Generally, we have the values ranging from 5 to 40 dB or higher than that is acceptable. 40 dB indicates that only 1% of the signal is reflected back from the load. Remaining 99% are transmitted from the source to the generator. Now let us find the standing wave ratio. So we can define the standing wave ratio by the ratio of voltage max to the voltage min, or current max to the current min, which is going to be 1 plus magnitude of reflection coefficient divided by 1 minus magnitude of reflection coefficient. If suppose I was given the VSWR, I want to find the magnitude of reflection coefficient, means it is going to be VSWR minus 1 divided by VSWR plus 1, that is S minus 1 divided by S plus 1. Here I can define I max as V max by Z naught and I min as V min by Z naught. Okay, we know that V equal to IR, right, in the relation. Generally, input impedance has a maxima and minimum value, okay, that occurs at the maximum and minimum of the voltage standing wave. Whenever voltage wave is having the maximum value, I will get the magnitude of input impedance max. Okay, that is going to be equal to V max by I min. When voltage is maximum, current will be minimum, and that is going to be equal to S into Z naught, relating these two expressions that we have written, right? The first one and here in the sentence it have written S into Z naught. Maximum is VSWR multiplied with characteristic impedance. Minimum value of input impedance is characteristic impedance divided by VSWR. That is going to be equal to V min by I max. Now we are going to see how the voltage max and minima are occurring by taking a lossless line which is having a characteristic impedance as 50 ohm and which is terminated by a purely resistive load, that is ZL equal to 100 ohm. In that case, the voltage measured at the load will be 100 volt. Okay, this 100 volt will repeat after lambda by 2. Another voltage max I will get. Okay, these are the standing waves created because of the mismatch between the load and the characteristic impedance. There is a mismatch, right? Here it is 100, here it is 50. So because of the mismatch, standing waves are created where we are able to see voltage max, min. Successive voltage max will occur at of lambda by 2, as we can see here. Okay, wavelength, in terms of wavelength, and between one V max and one voltage max and voltage minimum will occur at lambda by 4. Okay, and this I can see in terms of current also. Whenever voltage is maximum, what we observed in the previous expression, current is minimum, right? So the current minimum is occurring. Okay, now let us find the average power of a transmission line. So the average power is nothing but half of the real part of the phasor form of voltage at any point on the line, as well as multiplied by the complex conjugate of the phasor form of current. Here the factor 1 by 2 comes because we are dealing with the peak to peak values instead of the RMS value. We know that V peak to peak is nothing but V RMS by root 2, right? And we apply for current also IRMS by root 2, means 1 by root 2 into 1 by root 2 will become 1 by 2, since power is nothing but V into I. Okay, PPP into I peak to peak, we are going to product it, and we are going to take the real part of the voltage, okay, at the distance L from the load, similarly multiplied by conjugate of current term at the distance L from the load. This we already computed previous session for finding the input impedance. So we are going to substitute along with the condition that this reflected voltage is written in the term of reflection coefficient and incident voltage. So they have written here, and since it's a lossless line, we are going to take gamma as nothing but j beta. We are considering alpha 0, and if you do the conjugate multiplications, we get a into a star is magnitude of a square, right? And neglecting the imaginary part, we get average power as magnitude of incident voltage the whole square divided by twice the characteristic impedance into 1 minus reflection. coefficient whole square. So this is the average power is delivered to the load. So the transmitted power is nothing but is the incident power minus reflected power. Why it is minus reflected power? Because it is negative traveling wave, right? This average power that is delivered to the load is going to be a constant and does not depend on the length of the line since it's lossless line. And here maximum power when it can be delivered to the load when my reflection is 0. When there is no reflection, means reflection coefficient is 0, I can get maximum power delivered at the load. Hope you understood how to find the reflection coefficient gamma and VSWR. Yes, and how the voltage max and minima occurring, what are the distance between successive max and max and min, okay, locations, what is the distance we saw. Finally we computed the average power delivered to the load. Thank you everyone, we will meet in the next session.